Yes.
Yep.
Oh, okay. So the matrix is.
Just show you here the whiteboard. Yep, I've done.
Cool. It is. Oops. 0.8.
Yep.
0.2.
Oh, it's Markov, right? Markov.
Yes. It's the zombie humans.
Oh, who eat whom?
Exactly. Predator prey.
Yeah.
So I can solve that okay, which is to skip a few steps, which I know is probably not ideal, but we're going to get our.
That's right.
This.
That's right. Yeah.
And then, so let's call that A. So the determinant.
That would be not A. It would be the A minus lambda and the unit vector. You see?
Yes.
So
yes.
this
Yes.
A. This is A or Markov matrix itself.
Right. Okay. Yep.
Okay.
So the determinant of A minus lambda times identity has to equal 0.
That's right. That criteria. That is a condition you have to obey.
Yes. So we're going to have. Oops. Interesting feedback. 0.8 lambda. 0.9 lambda.
Yep.
Take.
Do you mean minor? Do you have the minor?
Oh, sorry.
Minor.
Sorry. Yep.
Yeah, a minor.
Yep.
Yeah.
Minus take 0.1 times 0.2.
Yep.
So then we go to, I think that's 0.72. Let's skip a few.
That's be lambda square, right? Lambda square. It's coefficient. Not yet. It's just lambda.
No, not yet.
Just lambda. Just lambda.
Okay.
Just lambda,
I was
right?
going to say 1 point. That's 0.72.
Oh,
so
it's that's
times
this is coefficient. Sorry, it's coefficient.
Yeah. Plus lambda squared.
So that is the sum of the two. Yeah. Okay. That's the sum of two.
0.02.
Yep.
Then we're going to have our full equation is going to be lambda squared. Make 1.7 lambda plus 0.7.
Yeah. That must be equal to 0. It's quadratical, right? Quadratical.
Yes, equals 0.
Yep.
So our A is 1, B equals 1.7.
Oh, you got it.
C.
Oh, is it just the coefficients?
Yeah, just the coefficients. And then we've got,
sorry.
Oops. Let's say lambda equals negative B plus or minus.
Yep.
4AC. Sorry. Oops. That's not correct.
B squared. B squared.
Yeah, got a little bit ahead of myself.
Okay.
So B squared. Take 4AC all over 2A equals 1.7 plus or minus
B squared.
Yeah. Take 4 times 1 times 0.7 equals. We're going to end up with. I remember because I did the calculation that I prepared earlier. Is I think it's 0.3.
Mm-hmm. So all right, you got two values, right?
Yeah. Now, I just don't know what to do with these.
One is 0. One is 1. One is 1.
One
Yeah,
or
lambda. Can you say
0.7?
lambda equal to 1? And another one,
Mm-hmm.
another eigenvalue is equal to 0.7. Oh, not too bad. Not too bad. So that is your next step. You're going to work out the eigenfunction, eigenvector, right?
Yes.
So
And
you have to substitute this value into the equation.
I see. So into this equation.
So basically, you have assumed. Can we just assuming? We just do it one by one. We have make assumption, assuming that
Mm-hmm.
the first eigenvector will equal to say xy, xy.
Mm-hmm.
So therefore, if you remember how did we solve this problem? We got so that we're equal to a minus lambda multiply the not unit matrix, identity matrix.
Mm-hmm.
Identity matrix multiply these particular vectors. Can you see?
Yes.
And that equal to 0. Okay.
Yes.
So if you substitute that, you have done that. Can we just work out these matrices, which is the difference between these two? So basically, we have to. Can we just consider lambda equal to lambda 1 equal to 1? Can we solve this first?
Mm-hmm.
Okay. If solve that first, we have substitute lambda into this equation. So basically, these will be these matrices. This matrix will be equal to 0.8 take away 1. Okay.
Yep.
0.1, and that's 0.2, and then that 0.9 take away a 1.
Mm-hmm.
So I'm talking about this the coefficient. Can we just simplify that? So that would be 0. Negative, right? Negative 0.2.
Yes.
This be negative 2. And that is
Mm-hmm.
remain the same 1, and that would be negative 1, negative 1, 0.1, negative.
Yes.
Okay, so that is a matrix. Okay, and
Mm-hmm.
that a little bit crowded here. But what you can do next? Can we just solve that? Can we just rewrite that equation? So if you substitute this coefficient into that formula, we got these formulas. We got negative 0.2x, right, plus 0.1 y. Do you know xy?
Mm-hmm.
Xy are two components for this first eigenvector.
Uh-huh.
Okay.
Yes.
The second linear equation that will equal to 0. Second equation will be 0.2 positive 0.2 positive x, and
Mm-hmm.
take away 0.1 y
Mm-hmm.
equal to 0. So from the matrix form, we got two simultaneous linear equations.
Yes.
Okay, and from this you can see x and y are dependent. X, y, and are dependent. So from both equation, see if you just multiply, can we just multiply 10? If multiply
Mm-hmm.
10 there, so if we just multiply 10, that makes it look better. Actually, we can multiply 10 from beginning. Doesn't matter. We have gone that far.
Ah.
If you
Yeah.
multiply 10, we got integers. We don't want to see the decimal. Okay. So in
Mm-hmm.
this way, I got a small space here. We got what? We got negative 2x, okay, plus y equal to 0.
Mm-hmm.
And the next second equation became, because multiply 10,
Mm-hmm.
2x minus y equal to 0. Okay.
Yeah.
From these two equations, either of them will give this simple relation that is 2x equal to y. Okay.
Yeah.
Can you see that? So let's turn to the page. So this is our assumption. So for lambda equal to 1, we assume the first eigenvalue can be written as x and y. Okay. By solving this equation from this equation, from this a minus lambda 1 identity, multiply this vector equal to 0, and we got the x and y are dependent, not independent,
Mm-hmm.
dependent. So from this one, we obtained that 2x equal to y. Okay, that is important. So that is a thing in this way. Therefore, this is equation 1, equation 2. So if we just do substitution, if substitute 2, that is our solution. Although we don't know x and y, but we know their dependence, right? If you substitute this into equation 1, what can we obtain? We can, for example, we can get rid of y. We can rewrite y as 2x. So this vector, the first eigenvalue, can be written as, we keep x, okay? Then y will become 2x. Can you see? We just replace y by the 2x, which is obtained from this criteria for solving eigenvalue. So we can factorize. Can we factorize x here? Say we got this simplified column vector. It's a vector, okay? It's actually you can make the unit vector, but it at least it's one of the bases. So one of these bases. That's this word can respond. So we in that way we solve the problem because the reason we use integer here because it's easier to count, right? Easier to trace. So in other words, this we can only determine the direction of the eigenvector. Okay. So if you want to draw the diagram here graphically, that's what I'm planning to talk about today, about the graphical meaning. So basically, you remember, if you use x and y, and apparently this particular vector is 1, 2. Where is 1, 2? So if this is can you participate? This is 1. Can you see?
Maybe it's
here's a 2. Here's 2. That is y. Oh, this is just two perpendicular direction. We don't know called x, y because otherwise you're confused with this x, y notation here. Yeah, that's right. So basically, if that is a coordinate, now if we just treat it as a vector because the basis is after all is a vector, so that would be the base. That would be one of the eigenvalue. And this eigenvalue doesn't belong to the eigenvalue in this coordinate. We know ij, okay, I and j can represent this eigenvalue. So basically, another thing we can tell you, this is eigenvalue in the representation of x, y, not x, y, but I and j rather, okay. So that is when you're doing when you're trying to solve the algebra, you have to choose proper letters. Okay. Now, don't confuse with x, y here, because after all, we can use any letter to represent this unknown eigenvalue. Can you say a, b? Okay. Even we use this a, b, we can still solve it. We just replace a. If, for example, at the beginning, I didn't use x and y to represent two components. I can use any letter, a and b. So in this way, we can still solve that. This first eigenvalue were equal to a. Can you see that?
The first eigenvector?
No, this is the first eigenvector can respond to lambda equal to 1. Yes, that's right.
Yep.
They are all associated. Yes. So the reason I say before I go further, I say in algebra you can use any letters. If I didn't use x, y, I could also use a and b. Okay.
Sure.
Which would be good for my discussing, because here I just can we call the capital X? I was trying to keep keep a distance from x, y. Don't get confused. Sure. So in this x, y plane, we know that I and j are their bases, right? So in this case, they got two bases in this x, y coordinate. So this is I, right? And this is j. You see, it's I and j. So in other words, it's come to our basic idea that any vector can be written as components form in a choosing coordinate. I just trying to take this chance to get some ideas through. So that is I. Remember, this is J. So in other words, in that way, we can rewrite this vector. We can rewrite this vector correspond to lambda 1 equal to 1. Can be written as, can you see? We can make the sum. You see, we can use 1 and 2. We can rewrite it as, so if I use a bracket here, we factorize that. That becomes 1 multiply 1, 0, and then plus, that's you are familiar with this notation, right? 0 and 1, can you see?
Yes.
So in this way, what we have done, we just end up with this I, can you see? Plus 2J. So okay. Of course, this I and J are the unit vector, the basis, but they are different. Okay, they are different for the eigenvalue we are looking for.
Right. Is this the eigenbasis?
I and J, I and J has nothing to do with this particular one. We just happen to choose these two, so these are the basis. In this particular representation, So we don't have to consider this. We don't have to mention this I and J, because our objective in this case is looking for the eigenvalue of this Markov matrix, which is A. Can you see that? Okay.
Yep.
So that is how to obtain the first eigenvalue, eigenvector.
Yep.
Okay. Which noticeably is different from the I and J, although they are dependent on I and J. Can you see these can, so basically what does that mean is that the first eigenvector can be written as a combination. Can we see that is AI plus 2AJ.
Yep.
Okay. Let's just review. I write this form just to review what we have learned before. Do you want to try the second eigenvalue?
Sure.
What is second value is 0.2?
0.7.
0.7, okay.
Yes.
Again,
so,
can we just assume it first? We just assuming. This time I use A and B again. It doesn't matter, you can use C and D, right? Can we use C and D? Can we use
yep.
We can use the second eigenvector. Can be used and C and D, doesn't matter. We can use C and D, just two numbers.
Sure.
Okay.
Okay.
Do you want to try?
So, sure. So it's going to be
that's the coefficient. Yeah, that's coefficient. Take away of 0.7. Yep, that's right. Yep.
So that's going to be equals.
Yeah, you can simplify that before we solve the linear equations.
Yep, 0.1, 0.2.
Okay, got all positive, right? Now, can we do something simple? Can we just multiply the 10 to get rid of the decimal? Yeah, we can get rid. Can we get rid? Yeah, get rid of the decimal. We divide by 10. Multiply.
Yep. Cool.
Yeah, so you have put a
Um,
10 here. Can we put a 10 here? We put a 10 in front. 1 over
yes,
10. 1
yes.
over 10.
Yep.
Oh, that's
So
much
the next,
simpler. Yeah.
much simpler. So the next step is going to be, so it's going to be this is going to be, we're going to be multiplying something by CD.
Yeah.
And it's going to be,
Can you recall the original form? So basically,
yes.
we are looking for this solution. So this is A. So this is coefficient. So basically, I can just follow you from here. This is our A. So we are looking for 1, 2, 1, 2, right?
Yes.
Okay, 1, 2, 1, 2. And then multiply the U2, which is C and D. Can you see? C and D.
Mm-hmm.
So once we got this coefficient matrix for coefficients, then we can rewrite this matrix form into a pair of simultaneous linear equations.
I see. Okay, so that's 1, 2, 1,
Yep,
2, CD
that's right.
equals 0. So therefore,
You can get rid of now. You don't have to write a matrix
sorry.
form. You just write
Yep.
algebra form now.
Sure.
That is it.
So 1C plus 1D
Yep,
equals 0.
that's right.
2C plus 2D equals 0 as well.
Yes, that is simultaneous equation. Yes, we can solve that.
Yeah,
They're identical, right? Can you see the two equations are identical?
yes.
Because you
Yes.
can, for example, for this one, if you just divide it by 2, they became original from equation 1. Can we write it equation 1 here, equation 2?
Yeah.
Now, just need a bit of time. How to solve the C and D? C and D are unknown.
Yes. We need to. Well, I feel like C and D can be -1 or 1, but I don't actually know how to solve.
Well, you can't.
Solve it properly.
As before, we cannot solve the C and D, but we can find their dependence. Do you understand?
Yes.
Can we see?
Okay.
Can we just write down? So from equation 1, what we have is that C equal to -D, right? Can we put equation 4? How about from equation 2, what we can obtain? What is the relation between C and D?
D equals
We got
-C.
2C equal to -2D. Can you see?
Yeah. Yep. Yep.
And we can cancel this 2. We can divide it 2 on both sides. We got a similar. We got exactly the same relation.
Right.
Make sense?
Yes. Yes, it does.
Yeah, this is where some students stopped because they can't you can't see because they didn't see the direct concrete result. But we are not looking for the absolute value for C and D because as we did before, just in lambda 1, we cannot fully determine the vector, the eigenvalue, the eigenvector. However, we are able to find their direction. That's more important. Okay.
Yes.
So from this one, we get the same equation. Can you see? C equal to -D, which is identical. So both 4 and 5 give identical relations. Okay. Well, you can use either of them to substitute this into our equation here. So therefore, I give you one more step. In this case, to find the direction of the second eigenvector, you can do substitution. I see C and D. You can keep either C or D and factorize it. Which one would you like to keep? Doesn't matter. You can keep C. You can keep D.
Let's keep C.
Okay, keep C. Okay. Well, if you keep C, you can continue. What would be the D in terms of C?
In terms of C, it would be -C.
Yes. Okay, one more step.
Yes.
One more step. You got C. You got C. Identical. Can you see the cofactor? You need to you can factorize that.
Oh, The cofactor is.
Can we write it as a 1 multiply C, okay? And negative 1 multiply C. Can you see the cofactor now? C is cofactor.
Yes.
Okay. Okay.
Yes.
So what can you do with cofactors?
You can take them outside. So
yes.
Okay. So
yes,
it's going
please.
to,
Yeah.
So it's going to be C1 -1.
Yep. You have done it. That's the second vector, second eigenvector. You have done that.
I see. Okay. Yep.
So that's important progress. Okay, let's get a sum up. So basically we had matrix. Did you call A, right? The A is 0.9. Can you just remind me, is 0.9?
Yep. 0.8.
0.8 rather. Okay, 0.2 then. How about another vector?
Yep.
How?
That was 0.1 and then
okay.
0.9.
Good. Okay. From where we got the solution of lambda 1 and lambda 2. So one is 1, another is 0.8, right? 0.2?
0.7.
0.7, okay. And from there, we got two eigenvalue now. Eigenvector. So 1 and 2. Although there's constant, okay? There's constant, so it doesn't matter. Can we go to A? Can we go to C? Okay. So we got, you got 1 and 2? 1 and 2?
Yeah.
What is this?
-1 and 1? Or 1 and -1?
1 and -1. 1 and -1.
Yeah.
Okay, that's enough. That's enough. So that is a big job. Okay, that is a big deal in the big part in the linear algebra course, and the students are required to find the eigenvalue and the eigenvectors. Okay,
Yes.
what can we do? What can we do with this eigenvalue vector? Bear in mind our objective is diagonalize. Do you know this formula?
Yes.
We mentioned it before.
We did.
Yes. We are looking for diagonal, D for diagonal, D for diagonal. In this particular case, we know what is a D now. D would be exactly equal to the lambda 1 and lambda 2, which is diagonal. Okay. So that would be, can we just substitute the number? One is 1, another is 0.2, right? 7, sorry, 0.7.
Yep.
That is what we call the diagonal. That's a big deal because we can reduce. Oh, by the way, I'm watching my old footage. I took the footage 30 years ago in Moorabbin Airport in Melbourne. It's it's just a pilot training company who I happen to be there to make some video for them. Okay, I'm just watching the footage and they have the flying formation. All of a sudden, I heard that background voice. They are mentioning is echelon. Okay, echelon. Okay, it's echelon formation. It's very quiet formation. So in the flying formation, echelon formation is a very special one. It means diagonal. Okay. You know the airplane? Yes, yes, this is echelon. So this is echelon. Okay, see? This is echelon. Okay, that makes sense.
I didn't know how to name.
I mean, either go that way, or you can go probably make it more like our case. See, this airplane go to one direction. Can you see?
Yep.
That's called echelon. Can you see? In our matrix, that's called echelon. You see?
Okay, that makes sense.
Oh, I'm surprised. 30 years ago.
I'm going to forget that now.
Yes, 30 years ago. I think at that time I didn't pay much attention to this word. Okay, because I'm thinking I'm working on totally different field, but actually that word mentioned. Okay, anyhow. So echelon, so diagonal is echelon as well. Okay, it's actually simpler than that. So echelon is diagonal. D for diagonal. Big deal. Diagonal. Diagonal, right? Diagonal. So diagonal is a part of echelon, right? Echelon. That's everything getting. So echelon is even simpler. Okay. Okay. So that's good deal. Oh, they give me the 10 minutes. They must have a robot working behind. It's very strange. I mean, they give me this warning for you, not for other students. I don't know why. Perhaps
Who knows?
they realize this is a non-linear algebra course.
Yes, they have something against linear algebra, perhaps.
Okay. Anyway, doesn't matter. We start in 10 minutes. Doesn't matter.
All good.
So this
All good.
one now that what I'm looking for. So in other words, next time when we're trying to say that formula, this very important formula, will allowed us to work out. So we now work. So when we work out the n a to power of n, for example, how many after many each year these two species eat each other, okay, and we don't know what would happen at the end. who will be survive and who will be extinct, we don't know.
Yes.
And that be turned into the question how to find this diagonal to the power of n.
Mm-hmm.
Can you see that?
I see.
Now, if
yes,
you
but the diagonal isn't just the. It's not just the eigenvalues. It's a. It's the diagonal. It's a.
That's right. So it's much. It simplifies the problem solving greatly. For example, if you just dealing with a square, 0.9, 0.2, 0.1, 0.9. If you just use doing square, you have to. Do you want to try? Which is more efficient? 0.9, 0.2. That is required to predict what's going on at the second year or at third year, right? At third year.
Yes.
Second year. So what would be population at the second year? You have multiplied these factors to the original population.
Yes, it's going to be quite difficult.
Yep, that's right. So 0.9, yep. 0.1, 0.22, and hang on, is 0.9 here, 0.9 here, yeah.
And okay. 0.8.
Okay, 0.8, that's right, 0.8, so there.
So that's going to be 0.8 squared plus 0. That's going to go there.
Yeah.
And then
this would be I write down 0.8 multiplied 0.2. No, 0.7. Sorry, 0.7. Oh, 0.9. Yes. 0.9. Yeah.
Yes. Sorry. Then.
Oh, they got quite involved, this calculation.
Yes. Oh, good. And then this one's going to be 0.2 times 0.8 plus
0.9. 0.9.
Yep. 0.9 times 0.2.
Yep.
And then 0.1 times 0.8.
Yeah.
8 plus 0.
No. 0. Hang on. That particular one 0.2. You say, did you choose this one?
Sorry. Sorry. Yeah.
Hang on. You are right. Hang on. First one is first you have to use the first column. So that's 0.8 multiplied 0.8. Can you see? 0.8. Can you see? Can you rewrite this part? This should be 0.8. 0.8. Huh?
I see.
No. Huh? 0.8 multiplied 0.1. You are right.
Yes.
You are right. Is this a plus or a product?
Sorry.
Yeah, it should be multiplied. Product. Yeah, that's right.
Yeah.
Second would be 0.1 multiplied 0.9. Yeah.
Yes. 0.9 times 0.1.
Yep.
And finally, 0.9 times 0.8. 0.9 times 0.2? No.
0.2 multiply 0.1. Can you see? You use this one. You use this number, multiply this number first. So this 0.2 multiply 0.1.
Yep.
This is nothing to do with 0.9. So this is, can we rewrite this part? Yeah, 0.2. Yeah, that's right. And plus
0.9 squared.
Yep, 0.9 squared. Yeah. Whoa, have fun. Oh.
Okay, so this is going to be 0.8. I think I need a calculator for this one. 2 seconds.
Yeah.
All right, so that's going to be 0.8. 0.8. That's going to be 0.64 plus 2.
Yeah.
It's going to be 0.16 plus. Oh, my handwriting's so messy, I don't even know what this is.
It's all right. It's all right. And
0.2, 0. I think that's a 9. Is this a 9?
Yes. What 0.8 multiply 0.2, 1.16.
Ah, yep, again. Yes. Oh. 0.8. So is this just the same? Sorry. No.
Doesn't matter, Patrick. It doesn't matter because you know it's tedious, okay? But if you can do practice, you can practice after that. What I can show you, I will show you the advantage of using the diagonal. After diagonal that matrix, what is the simplicity we can find here? Can we just go to this time? We use a metric square, but we use a diagonal. So that is 1 and 0.7. Okay. Can you work out this one? Can you work out this product? So it's 1, 0, and 0 and 0.7.
Yes, absolutely.
Yeah, 1, 0, 0, and 0.7. It's just one step instead of 0.
Definitely.
Yeah. Square? Yeah, you have done that. You have done that. Yeah, that's right. So you can see how faster. It's like,
yeah, definitely.
This just like the car driving at 60 kilometer per hour, and this is a Ferrari. Can you see?
Definitely. Yes.
Okay, that's how it works. And if you have time, perhaps you can try to see if this does happen. Okay, how can we just, for example, we can do one more exercise. See, we know that the A will equal to the P's transformation matrix. This diagonal is P inverse. All right. In our case, D has been determined by the 2 eigenvalue, that's 1 and 0.8, right?
Yep.
0.8. Is that 0.8?
0.7.
0.7 rather, yeah. 0.7. So, and we also know that P can be constructed. P can be constructed by these 2 eigenvalue, eigenvalue 1 and eigenvalue 2. That's my notation, not very formal.
Yep.
Do you remember that notation?
Yep.
One is 1, 2, right?
Yep.
1, 2, and that is negative 1. Can you see?
Yep.
Okay. So how about, do you remember how to work out the inverse?
Yes, there's some swapping.
Yeah, you're swapping. So you got determinant, right? Determinant 1, 2, 1, negative 1.